Today we are going to have a very quick revision lecture. We are going to check all our chapters. Chapter 1, it was speaking about soil classification. In soil classification, we have studied the three-phase diagram. Three-phase diagram, it means that the solid and water and the air of the material, what is required. Soil is very complicated, it is very random, it is very different from any other engineering material. So we have to try to approximate this soil into something that we can deal with. I cannot deal with this shape, but I can deal with this shape. If I say that I have a portion of air, a portion of water, a portion of solid, then I know the properties of these three materials alone, so I can approximate or try to deduce some equations based on this presentation of the soil. So the three-phase diagram is the first step for me to try to transfer the soil from a random material that I cannot simulate into numbers and figures that I can insert in any equation and get parameters for the soil. So this is what we need. This is the cases. This is the three-phase diagram. This is a case of fully saturated soil. It means that water filled all the gaps and the voids, so this is only water, or something that I took the sample, put it in an oven, so all of the water evaporated and the remaining will be just solid and air. And so on. These are few relations that were deduced based on this three-phase diagram. Something called void ratio. What is the definition of void ratio? You can check it. Of course, we're not going to waste time in this. This is what is the total weight of the soil, what is the total weight of dry soil, what is the total weight, what is the water content of wet soil, and so on. Many parameters. You will know the importance of these parameters when you go ahead and you find that you need some parameters in your design. What is porosity? What is the degree of saturation of soil? And so on. Lots of parameters that we have studied in this chapter. Based on this, we have few equations here. By the way, these equations, you will find some of them in your formula sheet that you may use, so you have to check what you have and what you don't have. So these are all derived equations, so that I can calculate anything from any other thing. This is an example. Of course, anything that is given as an example is very important, because in an exam I would just try to modify few numbers so that I know that you know that how to calculate, use this equation, and usually I give you the equation in the question itself, plus having it in the formula sheet. In something like this, I will say give you that n equal e over 1 plus e. It will be given in the question itself, and so on. These are all properties for the soil that we need to understand. This chart is very important, because it give you a presentation for the soil in case of adding water. What is shrinkage limit, what is plastic limit, what is liquid limit, because these three limits are three famous tests that are conducted in the lab. You go to the lab, you conduct a test called shrinkage limit, plastic limit, liquid limit. What are these three tests? You get values. So now I started to classify soil. Instead of saying that this is very soft clay or soft clay, something that I cannot measure, I tell you that I have a clay with a liquid limit of so and so, and the plastic limit of so and so, and the shrinkage limit of so and so. By giving you these numbers, I transferred the thing that is very descriptive into numbers. So now we can compare soils together. If I give you a clay with liquid limit of 70 and another with a liquid limit of 40, then you can understand what is the physical properties of the clay, and so on. All of these are called Atterberg limits. These three limits are called Atterberg limits. So you have to understand this. Check the recorded lecture, check what was said for this figure, and check what is these Atterberg limits, what are they, liquid, plastic, and shrinkage. The test is just for info. These are the tests that are conducted in lab. I will not tell you, just give me how to conduct the test and you tell me that I bring a sample and I put, so I don't want this. I just need to know that these are the shapes. Suppose if you go to the lab once and you've seen this, then you have to know that this is the equipment used for liquid limit. How to conduct the test, you can read this anytime and go and conduct the test, or perform the test. So this is how the test is done. This is the plastic limit, how to conduct or perform the test. By the way, the plastic limit is very simple test. You can conduct it with your hands. You bring the sample, rub your hands together so that you put the clay into small threads with a certain thickness and so on. So it is a very simple test. And so on. These are still relation, plasticity index, relative consistency. These are important tests because they are used in one of the examples that will be given later. And so on. What is given in all of this chapter is mainly relations between soil parameters for different parameters. This example is important for engineers because it will tell you that if you need to bring soil from outside and to put it to fill an excavation in the soil, how much soil you need, because the soil will not be compacted, or it will be compacted on the other side with a different value. How many meter cubes that would you bring to fill the gap that you have or the void that you have. So there are some parameters. We use these parameters. By the way, this is an important example. We repeat this example for different, suppose I have a quarry which is the place from where you bring the new soil. I have in this place, they sell me the price for 1 meter, 13 pound, here 16 pound, here 22 pound. If I would say 13 pound Egyptian pound is the cheapest, but maybe the 16 is the cheapest because maybe this soil, the degree of compaction of this soil is different from this. So the amount that I will need will differ, and so on. So this is the idea about this, is that I am trying to check which type of soil to use, or which degree of compaction of soil to use to pay less for this. So this is an example. Then later we go into this is you may have some questions. What is the difference between residual soil and transported soil? This is defining the soil based on the origin of the soil. Was this soil all over its place from creation till now? It was in one place, or it was transported from one place to the other? Usually when soil is transported, it loses some of its strength. So usually a transported soil is less strong than a residual soil. So this is what another important. Something else, I may classify the soil based on its origin. Is it organic or is it inorganic? Of course, if it is organic soil, I don't use it because it is something that it will react with time, and it may lose a big portion of its volume. So I don't use organic soil, but I use inorganic soil. This is a classification based on the diameter of the grains of the soil. This is very important because when I say sand, clay, and it means just a specific range of diameter. So this is the case of cohesive soil, and here is cohesionless. Cohesionless is sand, gravel, and boulder. Cohesive soil is clay and silt, and so on. This is the sieve analysis test. You need just to know that a sieve analysis test is used to separate all diameters from each other to know the portion of each diameter of the soil, and so on. How to conduct this test for silt and clay, I cannot use sieve analysis. Instead of using the sieve analysis, I use another test called the hydrometer test or the sedimentation analysis test. This is based on having that when I take soil and put it in water, it will have density that differs based on the particle size of the soil. But you just need to know that the hydrometer replaces the sieve analysis in case of very fine grained soil like silt and clay. So this was the first lecture. The second lecture was the site investigation. In the site investigation, we said what is the importance of the site investigation, how to carry the site investigation, what are the different boreholes, test pits, and so on, everything related to this, how many boreholes I would conduct, what is the minimum number of boreholes. What is very important is that here for normal sites, I use one borehole for every 300 meters square. So if I have a site or a building that is 900 meters square, 3 boreholes would be enough. In this other table, it gives me the minimum depth of the boreholes. Usually it is the minimum depth is 10 meter, or it may be increased depending on your building. The depth of the borehole should cover the expected depth where the stress is going to reach in the soil. What is this expected depth? Usually we take the expected depth to be twice the width of the footing. If I have, this is the width of the footing, so twice the width would be the maximum that a considerable stress would reach the bottom of the soil. So twice the B is enough for a borehole, or something below the expected pile length. Suppose you have piles, then you go say 5 meters below this depth, and this is the depth of the boreholes, and so on. This is the test pits. Standard penetration test is also very important. What is the standard penetration test? How we do it very quickly without lots of details. So this is important. And similar one is called the CPT test, which is the comb penetration test that is done for clay soil. So the SPT is mainly for sand. It may be also used for clay, but it is mainly for sand. And CPT is mainly used for clay soil. There is something called the plate loading test. All of these are tests that are conducted on site. So these are very important because tests that are conducted on site are very important because they give me accurate values because the soil is in place, it was not moved, it was not disturbed, so it is very good. Another type is called the geophysical investigation, where something like the ultrasound or the sonar that you may conduct for yourself at any physician. It's the same, it's an equipment, you just pass it on the ground and try to send a wave and analyze the returning wave and so on to check what is the type of the soil and the depth of the soil below. And then finally we present all in a geotechnical report showing us what is the formation of the soil in this site and what is the layering and what are the soil parameters and so on. Then we went into the soil, water and permeability. Permeability is a very important issue in our case. So in permeability we have there are tests that may be conducted in the lab, and there are tests that may be conducted in the field and so on. Why we are studying permeability? Just to study the seepage. This is where we will start our first important question that usually come in any exam, which is drawing the flow diagram below the soil. You may have all of these are cases for soil. I just want to go to first to the flow diagram. Then yes, this is the flow net. If I have soil here, water here, and at the other side it is less, how will be the shape of the water that is going to pass by this? I'm not going to go into the details of the flow net because it is given in the lecture of the flow net, because it may take a full lecture to discuss how to draw a flow net, and you have already drawn a flow net in your coursework, so you're supposed to know it. The shape may be different. You may have something like this, you may have something like this, you may have something like the one that came in your coursework. All of them are very easy. You just, once you draw something like this, you just count the number of, as if they are squares here, just count the number of squares in this direction and count the number of squares in this direction, and the ratio between them is used to substitute in an equation, something like this one, K, which is the coefficient of permeability here. What is this coefficient? It is equal, where is the equation? Just check where is the equation. عاوز اخد نفسي بس لان انا تعبت. المنهج Okay, it's enough rest now. We'll continue. Okay, now we need to understand what is compaction. Because this is it will be one of our lectures. Compaction, it means that I'm trying to condensate the particles, make them very close to each other by expelling water. If I expel the water, it will be consolidation. If I expel some air, it will be just normal settlement. But expelling water in sand, it is also settlement, because it will be very rapid expelling of water. But expelling water in clay, it will take time. In this case, the definition is changed from settlement into consolidation. So consolidation is a settlement, but it takes longer time because the permeability of the soil is very low. This is the only difference. So what will happen? What will happen is that particles will come closer to each other and try to push either, first it will push the voids, then once it finishes the voids, it will start pushing the water in the voids till it reaches a condition where all the particles are stuck together I don't have any more voids that can be expelled out. This few cases they are gathered here in this one case. It give you in case what is called drained response and undrained response. What is the difference between drained and undrained? From the name, drained means I gave the soil time so that water would leave the sample. Undrained, it means that I prevented water from leaving the soil. How can I prevent it from leaving the soil? I just make a very quick loading. In this case, water cannot leave the soil. So how will the total stress be presented? This is the case for the drained and the undrained. How the volume will be presented? This, of course, if I add the stress here, the volume will decrease. But here the volume will decrease in a way different from this way, and so on. How is the pore water pressure going to be presented? This is for both cases. How the effective stress is going to be presented for both cases. If you understand these 8 figures, then you understand the drained and the undrained for all cases of water. So of course this was presented more details in the lecture. The lecture for the shear strength, we said that to understand first what is the shear strength. What are the shear strength parameters? The shear strength parameters are the C and the phi. The phi is mainly for sand, which is the angle of internal friction. And the C is for clay, and it is the cohesion between the soil. How to differentiate between both? Just check this figure. What is this? This is a piece of clay that was shaped to have this O-shaped figure. Can I do this with sand? No, I cannot do this with sand. I can only do this with clay. So it means that clay has something additional than sand. What is this something? It is the C, the cohesion. Particles can grab together to each other, can stick to each other just by, as if they are adhering to each other. If I bring sand and I pour it on the ground, what will happen? It will take this conical shape. How this conical shape happened? It happened because I have friction between the particles of the sand. If I put clay on the soil, on the ground, it will not take this shape anymore because it does not have any friction. So when you have cohesion, you can have this shape, you can have this shape. If you have friction, you can have this pyramid shape. So this is the comparison between the shape of the friction and the shape of the cohesion. Can I give you an example for something that does not have any friction and cohesion? Yes. Bring few beads, small beads, put them on the ground. You cannot stick them together, and you cannot put them in a pyramid shape. It means that when you put these beads on the ground, they are going to just fill the ground, just one layer on the ground. So this is a presentation for a soil that does not have any, it's imaginary soil. These are the particles of the soil that do not have any friction nor any cohesion. How to make these particles similar to these frictional particles? I will just take these, try to this samfara, just try to friction the surface, to make some roughness on this surface. If you add roughness to this surface, what will happen? When you put them together, you will find particles on each other, as if they are grabbing on each other's side. So this is adding friction to this soil. If I don't want to add friction and I want to add cohesion, just bring glue. Bring some glue, add them to these particles. When the glue starts to harden a little bit, try to do any shape, you can do any shape and the particles will stay together. So it means that cohesion is like the glue that fixes particles together. Friction is the roughness that you induce to the surface of the particles of the material. So sand has friction on the particles. Cohesion, clay, has some kind of electrical charges that glues the particles together. This is how you can understand. So if I know that now what is cohesion and what is friction, these are the main components that I need to calculate the frictional capacity of the soil, not the friction, the shear strength of the soil. So friction, it is measured by phi, the angle of internal friction. Cohesion is measured by C, which is the cohesion of between the particles. So these two together, they are presented in an equation. This is the equation that was given by scientists, that the shear strength of the soil equal to the normal stress of the soil multiplied by tan phi, the phi, the one that we have just discussed, plus C is the C. This is the C and this is the phi. So now we know what is the C and phi. We substitute for the C and we substitute for the phi. So the remaining will be sigma vertical, which is the vertical force on any soil. So knowing the vertical force on any soil, knowing the phi and the C of the soil, we can calculate the tau, which is the shear strength of the soil. This we used in checking your coursework number 1. We used this equation. What is important in the shear strength? To prevent all of these failures. All of these failures are shear strength failures, because this was the figure that we were discussing before the lecture, where we need to measure an angle. Here we need to measure an angle. معايا? So here, once I draw this equation that we've just discussed, we can measure this angle to be the phi of the soil, and measure this intercept with the 0 at the x-axis, with the y-axis, to get this C value. So I can measure the C and the phi of the soil using this test, which is the test here, not this one. This is slope stability. So I think that there is a drawing here for this test. We'll just go to it. I think, yes, this is the laboratory test. So this is this is our test. This is the direct shear test that we conducted on in the coursework. By the way, what you have done in the coursework is what you are going to do in the exams. So similar to what you have studied. As I said, any example that is solved with numbers, then you expect that it may be seen in an exam. So you have to check all of the examples that were given in all of the lectures. Anything that is solved with numbers, then it is similar to your exam, or it may be a candidate to be one of your exams problems. So this for the direct shear. The direct shear lecture is very, it is big, and it includes a lot of data. You need to check it, to read it, not from the review lecture. You have to check it very accurately from the lecture of your, for this, the recorded lecture for this. And so on. So this lecture, you have to check it from your lectures, recorded lectures, because it is very big. It cannot be covered in just part of a lecture. Slope stability. The theory behind the slope stability is very important. When to use slope stability and not to use slope stability. Maybe I can replace slope stability with retaining walls. But why slope stability? It helps you to have two levels in any engineering project. Suppose I want soil at a certain level and soil at another level. Then how to keep these two soils at the same level, at different level? Then I should add a wall in between or make a slope. So, but this slope should be safe. How to check that the slope is safe? I can check that slope is safe by doing analysis for these cases. Of course, in soil mechanics, if I'm not using a finite element program and I'm using the traditional theories, usually in the traditional theories, I have to propose the shape of failure to get how my problem will be solved. So if I have a slope like this, this may be a shape of failure. So we call it a slope failure because the failure happened in the slope. Or it may be a toe failure, that the failure happened here. Or it may be a base failure because it just extended beneath the base. Which one will happen? I don't know. I cannot guess. And is it this curved line, or is it a part of a circle, or maybe it is a slope where this is slope, this is slope, this is. There are millions of slopes and millions of shape of toe failure, because for the toe failure I know that it ends here, but it starts from where? From this point, this many points. The same for the base failure. So as you've seen, usually at the beginning of the geotechnical engineering, to calculate a problem like this, I had to solve this problem many times to get different safety factors. I will calculate this one and check the factor of safety, and I will calculate this and check the factor of safety, and then this and the factor of safety. And for each one of these, I will do cases for different slope failure, for different toe failures, for different base failures. Then I will end up having maybe 10, 20 cases. Each case takes a lot of time to do. And then I will choose the one with the minimum factor of safety to be the solution of this problem. Now programs can do this in very short time. So that's why nowadays we solve it using programs. So that's why in our scope, of course, we are not going to use a program, because program changes. Now we are using a program called the slope. Later you will, when you graduate and go to work, maybe another program will be there. So you have to understand the theory so that when you apply it to any program, you can know what is happening. So, and failure may not be just a circle. It may be ellipse. It may be a combination of different. Part of it is a straight line, part of it is curved, another part is curved. Lots of cases, more than you can imagine. So nowadays we are using programs, but to understand the theory, we just go to this case, try to, of course there are many theoretical cases, but we are going to take just what we call the method of slices. The method of slices depend on a specific theory. Instead of solving the problem as a whole, it divides the problem into specific columns. I will just go to this one here. Here is this one. This is the shape of this is the part that want to fall down, and the friction along this line, the friction and the cohesion along this line try to prevent it. So the shear strength equation try to prevent the failure, and the loads here try to induce the failure. I divide what is inducing the failure by what is or I divide what is preventing the failure by what is inducing the failure. I will get a factor of safety. This is the problem that you have to study. Problem like this, of course, in the exam you will not have many slices like this. You may have 3-4 slices in the maximum, and you will get all the numbers that you need to study, and you are going to study slice by slice. Of course, this this problem is solved in the recorded lecture, and you have a specific recorded lecture from UH for an example similar to the one that usually is come in the exam. So it is very important that you study it, understand it, so that you can apply it in any exam. The theory is that I have an equation, I have the factor of safety. This is the equation that I have to use. Instead of just calculating all of these, I just calculate these here for each slice. The slice number 1, I calculate all of the parameters. Slice number 2, calculate all of the parameters, and then go from the parameters to W cosine, W sine, and so on. All the factors that I need here. I need here W cosine, I need here W sine, I need here C multiplied by L, which is the length of the arc at the bottom, and so on. So I try to take all of these parameters, put them in a table, so that once I just add all the numbers for each slice here and the number for each slice here, divide them by each other to get the factor of safety. This is a straightforward problem. You just need to understand the theory of this problem and check by your hand at least one example solved till the end using by yourself, so that you can apply it if you face it in the exam. There are many other methods. There is Bishop's conventional method, there is Bishop regress method. All of these are different equations. Of course, here the factor of safety is a little bit more complicated. If I go to the regress method, it is the factor of safety is very more complicated, and so on. So the theory, the concept is the same, but the degree of complication is different. That's why in the exam we usually stick to the simplest way of calculation. Very important thing is how to increase the stability of the slope. This is one thing, how to increase the stability of the slope. So how to increase the stability of the slope? Of course, when I calculate here the factor of safety, this is the stability of the slope. If I have a factor of safety of 5, then this is a very stable slope. If I have a factor of safety of 0.7, 0.8, 0.9, this is unstable slope. So this is the factor of safety. So this is the factor of safety. How to increase the factor of safety, this is one thing, and how to improve the shape of the slope so that it can resist time and it is not eroded with time. This is another thing. It does not increase the factor of safety, but it increases the lifespan of the slope. So you have to understand what is the factor of safety. So methods to protect the slope is something, and to increase the factor of safety, this is another thing. Protecting the slope is just, if I just cover the slope with rock, cover it with any cultivation, just plants, plantation, pitching, adding small stones. This all, if I calculate the factor of safety before adding or after adding, maybe in one case it would be 1.5 and in the other case it will be 1.52. The difference is nothing. It's not considerable at all. But what is the difference? When I put something like this on top of the slope, it will resist wind, it will resist rain, it will resist lots of erosions, so that my slope will last a very long time in the same shape. But if I leave it to the environment, it will be eroded with time. So all of these are methods for compaction, for protection. It does not increase the factor of safety. But if I want to increase the factor of safety, what should I do? Maybe reduce the height of the slope. Reducing the height of the slope would reduce the factor of safety, would increase the factor of safety. Use a slope that is more, it is less steep. This will increase the factor of safety, and so on. So there are methods to increase the factor of safety, and there is method just to protect the slope. We have to differentiate between them, because some engineers, when you ask them to increase the factor of safety of the slope, he will tell you, I will add pitching. Pitching will not increase the factor of safety. It will just will increase it by 1%, nothing. But what is important, to add something that would increase the factor of safety. But pitching or covering with concrete is just to protect the slope. So this is important. Shotcrete is just concrete poured on the top of the slope to protect. All of these are for protection. Then this is an example. This example is similar to the example that is given to you in a separate lecture. You have to study both, and this table is very important. This is the factor of safety that is calculated based on this table. This is very important. Go to the other lecture. So now we are going to concentrate in the remaining of the lecture to discuss three things: compaction and settlement and consolidation settlement. These are the three things. Compaction, that will result in reducing the settlement, and consolidation settlement that would happen with time in clay. So what are these? What is compaction? Of course, I will just go to what are the types of settlement. We have three main types of settlement. Immediate settlement, this is the elastic settlement that happens when I just put the load. It mainly happens in sand, and it happens a little bit in clay. Then I have primary consolidation settlement. This primary consolidation settlement happens mainly in clay, where when I put the load, it will settle a little bit as immediate settlement, and the full load will happen later with time when consolidation starts to happen. When consolidation is finished, both immediate and consolidation settlement contributes to the major settlement of my soil. Later, I may have something called the creep settlement. Creep settlement is just the particles changing its orientation so that it would fit better, something like the puzzle. When you have a puzzle, if you just put it on the ground, it will fill a lot of area. But if you put each piece of puzzle in its place, it will take the smallest area. So this is exactly what is happening with creep. Particles are just changing its direction and orientation just to fit better in a smaller volume. So it takes longer time and the amount is not very considerable, so in many cases we do not calculate the creep settlement, and we just know that there may happen creep settlement with time, but it is not very big. So this is the definition of the three types of settlement, and so on. Yes, this is how to calculate the settlement. I need to calculate it based on something called the modulus of elasticity. This is a table giving a range of modulus of elasticity. Of course, you may have different tables in any other books. And this is something called the Poisson's ratio. It is needed in some equations and so on. And we go again to what we have studied in this lecture, I think, the lecture of the stresses. Yes, this one. This is the lecture of the stresses, and we said just this lecture where we have the different types of loading, wall, concentrated load, loaded area, and so on. All of these are given in just repeated here as a summary for the additional stresses that may affect, because these additional stresses is the ones that you are going to use in calculating the stresses on the soil and Newmark chart. Everything we said in the previous lecture, and this example is repeated again, and so on. So it is similar. And now how we can calculate the elastic settlement beneath a footing, and the equation. Of course, in any problem you will get, you will have you will be given the equation that is going to be used and the parameters that you are going to substitute in the equation. What is compaction? Now, we have studied up till now what is settlement. Settlement is the settlement that is going to happen. Can I prevent the settlement? Yes. How to prevent the settlement? By making settlement myself before it happened. It is as if I am settling the soil before the soil settles due to the future load. So I go to the soil, try to push the sample together, the particles, compact them together, so that later when it is subjected to load, the particles are already settled and it cannot go further, or if it go further, it will be a little amount. So compaction, this is the theory about compaction, is that you are just taking loose particles, put them together so that the voids are the minimum. These are some formulas that were presented in our lecture for our first lecture. I think it was here. Yes, all of these are the formulas that were used. Just here a repetition of some of these formulas and how to apply it in our work to calculate any geotechnical parameters that we need. This is something called standard Proctor test. These are all just for info, just know what are these tests. Of course, you don't need to, if a problem is not solved with numbers, then it is just given you for, just to know what are these formulas. Of course, you will have also this example is very important. Also, this example here is very this is yes, it is example. Anything that is solved is important. You have to study it, and so on. For this lecture, this is the sand cone test, and this is how to calculate the density of the soil. Of course, the sand cone and the cone cutter, both are small equipments that you use for calculation of the unit weight of soil, and you have it in our lab. This is just a quick review for compaction and settlement. Then we go to consolidation. As we said, consolidation is the settlement in case we have water. So if this is a sample and this is a porous plate above, porous plate below, if I apply load here, then the sample will settle immediately, if it can settle immediately. But suppose it is clay, then the water has to leave this sample. So with time, the water will leave the sample and the sample will start to settle. So this is what we do in the lab. We just put the load, put everything on top, and then just record the settlement that is happening maybe after 1 hour, 2 hours, 8 hours, and so on, till I reach maybe 24 hours or maybe few days, and so on. So once I reach this, I can draw the curve for the settlement, and this I'm going to use for the calculation of the consolidation settlement by using something called MV. MV is the modulus that I use to calculate. It's a simple way for calculating the consolidation settlement. You also have to refer to this lecture. What is the difference between over consolidation and normal consolidation and under consolidation? Normally consolidated soil, it's the soil that was never subjected to load that is higher than the existing load. The soil now, I have a soil, I push it with the load, and then I increase the load. Every year I increase the load. It means that every year I'm subjecting the soil to a new stress, but it has never faced this stress before. But suppose after stressing the soil, I remove the stress, and then later, after 1 year, I stressed it again. In this case, it will be called over-consolidated. Why over-consolidated? Because I'm stressing it with a stress that it faced a long time ago, but I'm doing it again. I usually compare it to human beings. If you are grown up, you are very well experienced, you are subjected to many problems in your life and stresses in your life. So when you face a new problem, it is similar to a problem that you have faced before. But if you are just freshly graduated or just a teenager, then you will find that you are facing problems for the first time in your life. So in this case, I can say that you are normally consolidated, but maybe an experienced person that maybe 50, 60 years old, he has already faced many stresses before, so he can face new stresses with better experience. So normally consolidated soil is the soil, a teenager soil. Over consolidated soil, it's grown up a little bit, so it has been subjected to stresses before. Under consolidated soil is an imaginary case. It is the opposite of over consolidated. I just don't want to go through it because it's it is very difficult to face an under consolidated soil. So just skip it. Now, how to calculate similar to before we calculated the settlement of a footing. Now I need to calculate the consolidation of a footing. It will be the same, but the difference will be in using an equation that is different from the equation that was used for settlement. For settlement, it was an equation with E. Here it is a little bit difference. I have some consolidation parameters instead of just the E of the soil. So it is just a simple procedure, but the difference will be in using a different equation for consolidation. يعني that's all. يعني there is another يعني accurate method for calculating the consolidation. It takes time into consideration. Here we were calculating the total consolidation, but I don't know how many years it would take to consolidate, or how many months it would take to consolidate. But there is another way where I take something called the time factor. I would include the time factor. So using this method, I can calculate that this will settle maybe after 1 year, 2 years, 40 years. It depends on the type of soil. There is also something called the drainage path. We said consolidation means that water is leaving the soil. How is the water going to leave the soil? I wanted to leave the clay. Leaving the clay to a clay, it is still within the clay. It means that if I have water here, and this is a clay layer, and I want this water to come from here to there, then water, if it is here, it will go this way, up. But up, there is another portion of water that is at this place. It will just push the water to the top, and this push the water will push the top and top and top till it goes here. And once it goes here, it faces sand, very high permeability. Water will just run away out of the soil. So the time will be taken from here to there. If I have sand at the bottom, it means that clay may lose the water by going from here to there, and from here to the bottom also. So in this case, it is double drainage. Water can go up or can go down. Here it is just simple one-way drainage in this direction. So this is the difference. This ends up our lectures for this term. Consolidation is important mainly as theory, to know the difference between consolidation and settlement and so on. Settlement is important in calculating the settlement itself of the footing, and so on. This is very important question usually in any exam, the slope stability. So in slope stability, we have to understand, of course, the theory behind slope stability and how to calculate the slope stability, and so on. All of your lecture, shear strength, you may have an example how to calculate the shear strength, similar to your coursework, and in total and effective stress, how to calculate the total and effective stress at the different layers. This is also important. Of course, this is very important, how to draw this diagram for different cases. So this is also important. Other these site investigation and soil classification, it is mainly for description of the soil and how the soil behaves and so on. This ends up our quick revision. Of course, quick revision is not a substitution for hearing the lectures for all chapters. Once you finish all of the lectures, then you can go to this lecture again just to summarize everything together. Thank you, and see you next term, inshallah.